Bond dissociation, entropy change when all the bonds of the same type in one mole of gaseous molecules are broken. When all the bonds of the same type in one mole of gaseous molecules are broken. Entropy change of atomization of an element. Entropy change of one mole of gaseous atoms is formed from an element in its standard state. Entropy change of atomization of a compound. Entropy change of one mole of compound in its standard states convert to gaseous atoms. First electron affinity, entropy change of one mole of gaseous 1 minus ions is formed from one mole of gaseous atoms. Second electron affinity, entropy change of one mole of gaseous 2 minus ions is formed from one mole of gaseous 1 minus ion. 1 minus ions. Entropy change of hydration, entropy change of one mole of aqueous ions is formed from one mole of gaseous ions. Entropy change of solution. Entropy change of one mole of solute is dissolved in enough solvent so that no further entropy change occurs on further dilution. Entropy change of one mole of solute is dissolved in enough solvent so that no further entropy change occurs on further dilution. Lattice entropy. What is it a measure of? Lattice entropy is a measure of ionic bond strength. Two types of lattice entropy of formation, lattice entropy of dissociation. Lattice entropy of formation, entropy change of one mole of a solid ionic compound is formed from its gaseous ions under standard state. Lattice entropy of dissociation, entropy change of one mole of a solid ionic compound is completely dissociated into its gaseous ions under standard conditions. State two key assumptions of purely ionic model of lattice. Assumes all ions are spherical. It also assumes it has a charge evenly distributed around them. Now, this bit most students would know. Assumes all ions are spherical, but this bit I don't think a lot of students would know, including myself. Have a charge evenly distributed around them. Why do some ionic compounds have covalent character? The idea that positive and negative ions in lattice are not, I said not spherical, they're not completely spherical. Yeah, they're not completely spherical. Therefore, the positive ions, they polarize the neighboring negative ions to different extents. So, positive and negative ions in lattice are not completely symmetrical, or not completely spherical, sorry. Therefore, positive ions polarize neighboring negative ions to different extents. More polarization, more covalent bonding, and therefore, as there's more polarization, it's going to have some covalent character. First electron affinity example, O gaseous plus E minus from O minus gaseous. Second electron affinity example, O minus gaseous plus E minus to form O2 minus gaseous. Now, if delta H is positive, entropy change and all of that, and gives free energy change. If delta H is negative and has a positive delta S, then delta G is always negative. Therefore, reactions are feasible at any temperature. If delta H is positive and has a negative delta S, then delta G is always positive. Therefore, reaction is not feasible at any temperature. And if you think about it, delta G is delta H minus T delta S. If delta G is delta H minus T delta S. If delta H is negative and you've got a positive delta S, well then, yeah, because temperature can't be negative, can it? So then you're doing a negative use of positive. And yeah, so delta G would always be negative. However, if delta H is positive and it has a negative delta S, then delta G is always positive. Therefore, reaction not feasible at any temperature. If delta H is positive and delta S is positive, what happens? So the reaction won't be feasible, but it will be at higher temperatures. So if delta H is positive and delta S is positive, reaction won't be feasible but will be at higher temperatures. If delta H is negative and delta S is negative, reaction will be feasible at lower temperatures, however, it won't be feasible at higher temperatures. Definition of entropy S, a measure of the number of ways particles can be arranged, and the number of ways energy can be shared between the particles. More disordered the particles, higher the entropy. More disordered the particles, higher the entropy. Definition of standard entropy of a substance, or you might see it as that. Standard entropy of a substance is entropy of 1 mole of that substance under standard condition. Entropy of 1 mole of that substance under standard conditions. State two things when a solid ionic lattice dissolves in water, what happens? The bonds between the ions break. This gives free ions, therefore positive, delta H, endothermic. Bonds between ions and water are made, negative, delta H, exothermic. And the entropy of solution is the overall effect on entropy of these two things. Delta H of solution, overall effect on entropy of these two things. And I just want to go through one more thing that I don't write down about solid, liquid, and gases. and entropy. More disordered particles, higher entropy. Now, I want to ask you guys a question. If you want to pause the video, which one would you expect to have the highest entropy? Solid, liquid, or gas? 3, 2, 1. The answer, yes, is going to be a gas. Because the thing about a solid is they're all tightly packed together. So it's not going to be, very disordered. So a measure of the number of ways particles can be arranged, but cannot barely be rearranged. A number of ways energy can be shared between particles, not really. A liquid, yes, it's got a bit more movement, a bit more disorder, therefore a slightly higher entropy. And gas, 100% is going to have the highest entropy out of the three, because gases are far apart. So the number of ways it can be arranged, unlimited, loads of ways, I meant to say, and the number of ways energy can be shared between particles are loads of ways as well, and therefore, and also because more disordered particles in gas, therefore higher the entropy.